So is it live now?
1 minute. Just.
Okay, good.
Should I start?
Maybe I'll just introduce the session first. So welcome everyone to session 4A, and we'll have 4 talks in this session on topics ranging from cut problems to deterministic constructions of expander graph. Each talk is going to have a 5-minute presentation followed by a 5 minutes of question and answer session. And if there are more questions, we can continue with the discussions at the end of the session. And I hope all the speakers can stay on for a little bit after the session to answer more audience questions. So our first talk is going to be by Jason Lee on the Kcut algorithm is optimal for the Kcut problem.
One sec. Sorry, let me close my door.
Okay, we are good to go then.
Can you see my screen? Am I screen sharing?
You should start sharing the screen.
One sec. Okay. Okay, dude. Is it ready?
Yeah, please start.
Okay, so this talk will be on the Kcut algorithm is optimal for Kcut. I'm Jason Lee from CMU, and these slides are by Anupam Gupta. So in this talk, we'll be considering the Kcut problem. So given a graph, we want to delete the min-weight set of edges to cut the graph into at least k pieces. So this is a generalization of the global min-cut problem, which is when k is 2. So throughout the talk, think of k as a large constant, say 100. So throughout the talk, we'll be considering the Kcut problem on 2 canonical graph classes, the cycle and the clique, to hopefully illustrate how the Kcut problem, how to hopefully motivate the Kcut problem. So for a cycle, the op is k because we can delete any k edges of the cycle to split the graph into k components. And the number of the min k cuts is n choose k. So throughout the talk, we'll be also considering like a number of min k cuts. So for a complete graph, to get opt, we need to cut off, the best way to split this graph into k pieces is by cutting off k-1 singletons. And this has size roughly n times k. And again, there's n choose k-1 many such cuts, which is again, roughly n choose k. So the 2 central problems we'll be considering are, one is a computational problem, algorithmic problem, which is how fast can we compute the Kcut? And the second one is a more combinatorics problem, an extremal problem, which is given a graph, how many min k cuts can there be? So prior work on this. So the most well-known result for this problem is the randomized algorithm by Karger and Stein, which is generalization of Karger's randomized contraction algorithm for the global min-cut problem. So recently, there's been some improvement in the work first by getting deterministic algorithm, and then by improving the factor 2 in the exponent to something slightly less. So in this work, there's a lower bound which reduces the clique problem to the Kcut problem. So assuming popular conjectures on the hardness of K-clique, it is believed that there's no faster algorithm than roughly n to the k time for the Kcut problem. Finally, for approximation algorithms, 2 approximations known, and it's hard to beat n2 minus epsilon. So in this talk, our main result is we have a randomized algorithm to find the Kcut problem and to find the Kcut in n to the k time. So this matches the lower bound that we based on the clique hardness. And our algorithm can also enumerate overall all the min k cuts. So we get also an extremal bound, which is also tight because of the cycle we saw. So what is this algorithm? So what is our algorithm? Turns out our algorithm will just be the original Karger-Stein randomized contraction algorithm. So the same algorithm, but we provide a better analysis. So let's begin with the Carter-Stein algorithm for Kcut. So it's very simple. For Kcut, all the algorithm does is it iteratively picks a random edge in the graph. Let's say the graph is unweighted for now. Picks a random edge in the graph and contracts it, and just repeats this until k vertices remain. And once there are k vertices left, every vertex, imagine uncontracting the graph from the k vertex graph to the original graph. Each contracted vertex induces a component in the final Kcut. So let us briefly go over the analysis that shows that this simple algorithm will find a given min Kcut with probably at least n to the minus 2k. So when r vertices remain, so for some r from n down to k, the probability that we fail, the probability that we contract an edge in opt, is exactly opt over the number of edges remaining, which is, so first I claim the numerator opt is at most the numerator here. And the reason is because what is one way to get a Kcut? One way to get a Kcut is by picking k minus 1 random vertices, a random k minus 1 random vertices in the graph. Sorry. One way to get a min Kcut is by picking the smallest k minus 1 vertices in the graph, span of k minus 1 degrees. And this is a valid Kcut. Opt can only be smaller. And similarly, the number of edges in the graph is just a simple counting argument, is also equal to this one in the denominator. So note that the average of smallest k minus 1 degrees is at most average of all the vertices. So we get this bound right here. And now this is the probability that we fail on any given iteration. So overall, the probability that we succeed is just the product of 1 minus this quantity over all r. These are independent over different r. So we can bound it as follows. So now what about the two examples? So how do we get an improvement over the n to the 2k here? So we want to kind of improve this analysis by a factor 2 somewhere. So for the cycle, note that opt over number of edges here is actually, it's actually much better than 2k over r. It's actually k times r here because opt is k, the number of edges is always r because any given time in the algorithm for the algorithm on the cycle, we still have a cycle remaining. So this is much less, we get this factor 2 here, and this improvement directly translates back to a n to the k time. So what about for a complete graph? Well, here it's a little trickier because for a complete graph, this analysis is tight in the sense that at the very beginning, when r is n, the analysis so far is tight, and we get a factor 2 here that we cannot remove. So how do you beat this factor? Then the key idea in our paper is that after a while, this worst case tight example cannot hold over all r. It can hold when r is n. It might hold when r is n, but when r gets lower and lower, it is very unlikely to hold at later stages of the algorithm. In other words, after a while, for the clique, for example, after a while, most vertices will actually have a degree at least 2n and not just n. So for the rest of the talk, I'll illustrate.
Yeah, yes, and we need to finish here because this is way over time, and we.
Okay, sorry. Okay. Are any questions then?
We do have time for 1 or 2 quick questions right now.
I've got one.
Okay. Yeah.
Should I use the Q&A thing or?
You can go ahead and ask the question.
Sure. I'm just wondering if this all extends to results on approximately minimum cuts as well. It seems like it ought to if you're just bounding the number of edges.
Yeah, it does. So let me go to the last slide. Whoops. Yeah, so everything does work for approximate, and we didn't include the result for this paper, but we have an improvement that essentially gets, I think, n to the alpha k for alpha approximate cuts.
Good.
So this is also known for approximate.
although that means that we now have this sort of incomparable, like there's also this n to the floor of 2 alpha or something like that, which is sometimes going to be better than alpha k and sometimes worse, where I wonder which is the right answer, right?
Right, that's true, yeah. I guess to get the floor, we need to like probably shift to this tree packing kind of approach. Right?
Mm-hmm.
Because this one's more continuous and it's hard to get this floor value.
Yeah, although the like the Nash Williams perspective, you might be able to say some things about tree packings evolving the same way as you talk. I mean, you talk about the number of edges sticking around. You might also be able to argue that the number of trees that can be packed is much larger than the pessimistic Nash Williams bound.
Yeah, so that depends largely on which tree packing you pack. I think there are very bad tree packings in the sense that every single tree you pack will be bad in the sense that it will intersect like 2k minus 2 times. I think one example would be the clique and you pack like paths or something. Either you pack stars or you pack paths. I don't remember which one. But there are ways to like get bad tree packings.
But what I mean, only one of, if you consider only optimal tree packings, right? It should keep you away from that.
I think we should take maybe the rest of this discussion to the end of the session. And we're running a little bit late for the next talk, which happens to be from David himself. So let's take this discussion offline or just at the end of the session. So David, can you start sharing your screen? And also, yeah, yes, and, yeah, good. Okay, so our second talk is by David Karger on quadratic time algorithm for network reliability problem.
All right. Thanks, Sanjeev. So I also want to thank whoever planned the session to put me after Jason, because he was able to give a lot of the background that I can rely on without talking about it. So the problem I'm going to be talking about is the network reliability problem, where you're given an undirected graph. And you posit that the edges of that graph fail independently with some probability p, and you want to estimate the probability that the graph becomes disconnected. And of course, the disconnection of the graph occurs precisely when all of the edges of some cut of the graph fail. And I'll be using the usual parameters of m and n for the number of edges and vertices, and c for the minimum cut. And I'll use g of p to denote the result of that you get when you fail the edges of G with probability P. So be careful that this is not the result of including the edges with probability P. We're looking at the deletion model. So the ancient history of this problem is that it was one of the original Sharp problems. So we don't work on exact solutions for it, and instead we look for approximation schemes. And I did the first one in 1995 for estimating the probability that the graph becomes disconnected. And it had a runtime of roughly n to the 5th. And this problem lay fallow for about 20 years until Harris and Srinivasan came along with some really interesting observations about the problem that allowed them to improve the runtime to order n cubed. And those kind of attracted me back to thinking about it. And so I gave some other algorithms in 2016 and 2017 that inched the running time down to n to the 2.71. Also in 2017, Guo and Jerem finally gave a true approximation scheme for the reliability problem, which is the probability that the graph stays connected as opposed to the probability it gets unconnected. Since these are approximation algorithms, they don't actually, you can't reduce one to the other, and they're both interesting problems on their own. They use completely different techniques for reliability. So in this work, I'm going to be talking briefly about an order n squared runtime algorithm. It's based on giving a unbiased estimator for network reliability, which has a low relative variance. And the algorithm is really very simple. If the failure probability is large, then you use naive Monte Carlo estimation, where you just fail edges and test how often the graph gets disconnected. And if the failure probability is small, then you use the recursive contraction algorithm, which you just heard about. the Kurt algorithm, which builds two contracted subgraphs and then recursively estimates the reliability of each one and averages them. And so what this paper contributes is that n-squared runtime and also a clearer, simpler analysis of what's going on. But it doesn't do it through new algorithms. Really, this is a graph theory paper whose emphasis is on a sort of theory of random subgraphs. And I think it reveals a lot, it increases our understanding of how graphs evolve. You can imagine starting a graph with no edges because P is 1, all of the edges have failed, and then slowly shrinking P until it reaches 0 and all of the edges are present. And this paper sketches the evolution of that graph, where you start with everything disconnected, and eventually the probability P reaches a breakpoint, which is the place where the probability of being connected is a half. And so, of course, above the breakpoint, the graph is probably disconnected. As you pass through B, you begin a certain phase transition, which is a point where the graph is probably connected, but there's still a decent chance of having more than one cut fail. But shortly after that, you reach what I call a strong point, which is a point where disconnection is unlikely, but even more important, disconnection of more than one cut is incredibly unlikely. So when you get disconnected, it's generally through, it's almost certainly by only one cut. And this is the meat of the paper, is proving this and using an analysis based on sort of an analysis of the failure of cuts in the graph conditioned on the failure of other cuts in the graph. And so then what we prove is that this strong point, where you only have one cut failing, is very, very close to the breakpoint. So that in fact, even at the strong point, the unreliability, the probability of disconnection is still quite large. And so you can use the naive Monte Carlo estimation all the way down to the strong point. And the proof of this point is a sort of a direct study of the evolution of the graph's size and the minimum cut as edges arrive one at a time in a Poisson process. And so it actually has some relationship to the work that Jason just showed you, which also studies the evolution of graph sizes and degrees. So another perspective on this work is that there's certainly been plenty of work showing that as P gets small, the probability that the graph disconnects becomes negligible. That is the probability that you break into two components. And what this paper is contributing is that at about the same transition point, not only do you get a negligible probability of two components, but you also discover that all of the disconnection probability is in the two component case. And the probability that you get three components conditioned on there being a failure is still negligible. So the algorithm, as I mentioned, is very straightforward and basically involves a choice. If the failure probability of the graph is large, then you can compute it simply by running Monte Carlo simulations. You fail edges and with probability P, and you test if the graph is disconnected. And if it is, you count up how often that happens, and the fraction of times is an estimate for your probability. And this produces what's called an unbiased estimator, which is a standard way to estimate a quantity. It's some algorithm which generates a number whose expectation is the number that you want. And if you can get that expectation if you can get the variance of your algorithm to be small, then you're saying directly that you're probably close to the expectation, you're probably close to the number that you want. So if you have an unbiased estimator with the right expectation and a low relative variance, then you get an approximation scheme right away. And the runtime is, roughly speaking, the cost of one sample from your unbiased estimator times that relative variance, because you need to take multiple samples and average them in order to reduce that relative variance to a small quantity. Sorry, my watch has failed, so I can't see how much time I've spent. But I will say a few more things and then stop.
I think, David, you should try to wrap up within a minute or so.
Will do. So as I mentioned, if the reliability is large, then you use this naive Monte Carlo method. If it's small, we use a different estimator, which I can present as just a variant of the first one. So the naive method is to just try deleting every edge with probability P. So what I'm going to do instead is I'm going to do this in 2 stages. So first I'm going to weaken edges with probability Q, and then I'm going to delete them with probability P over Q. So you can see that this is exactly the same procedure, and it has the same probability of producing a disconnected graph. So I could use this as my unbiased estimator. But let me describe a different story. So here, I can imagine deleting the edges in the first stage, but now, or deleting these weak edges, now I know that the edges that remain are not going to be deleted in the final graph. So I can contract them before I proceed. And now I can put back the weakened edges that I deleted. And so this gives me a new graph that I'll call H, which is basically a sample that you get by deleting edges with probability Q. And so it is in this graph H that I will now delete edges with probability P over Q. And this graph H of P over Q is disconnected precisely when G of P is, because it's just another way of constructing G of P. So why is this interesting? Well, the point is that what this tells me is that the expected, that the probability that G gets connected is equal to the probability that H gets disconnected. But I have to average over all the possible graphs H that I might be constructing. And so this tells me that the expected value of H's unreliability is equal to the unreliability of G, which means that the unreliability of H is itself
Looks like we have lost David. It's completely frozen, it looks like. David, we had lost you, and you're muted right now. So,
apologies,
yeah.
I'm back.
Okay.
And I assume you lost, I assume I noticed right away when you lost me.
Yeah, we are really over time.
Yeah, I'm going to share, I'm going to wrap up just by giving my, shoot, where's that screen share? Just by jumping to the conclusions, because I think that this paper leaves some interesting open questions that I wanted to share. Whoops. The first one is whether there is a linear time algorithm for unreliability. I think that we've gotten quite far in understanding the evolution of graphs, and I think that with some more work, it should be possible to show that this unbiased estimator is effective over all values of the parameter Q, and that with some tweaking, I think it should be possible to turn it into a linear time estimator. There are also some interesting questions about multi-way cuts that I haven't investigated, the probability of the graph disconnecting into 3, 4, 5 pieces, and I think that the techniques here should apply there as well. Thanks very much.
Okay, thanks, David. So we'll just take one quick question, and then let's take the remaining questions after the talks, all 4 talks are over. So there's a question from Sandeep Silwal. What sort of graph problems besides, so let me just, okay. So the question from Sandeep Silwal is, what sort of graph problems besides connectivity would be an example of a monotone set system?
Sure, so the monotonicity property is simply saying that any subgraph of a graph in your system, or sorry, any supergraph of a graph in your system is also in your system. So the set of connected graphs has this property, right? If a particular subgraph of G is connected, then adding edges will only continue to make it connected, right? Other monotone properties would, for example, be the existence of a clique of a certain size, because adding edges won't make that clique go away. Existence of a Hamiltonian path. Also, I mean, sorry, I'm picking NP-hard examples, but anything with this structure that adding more edges does not change, does not take you away from having the artifact, is a monotone property.
Okay, so I think we should stop
Oh,
here.
and sorry, the answer to Chandra's question is not that I know of.
Okay, so so Chandra's question was, is there any deterministic algorithm for estimating reliability or unreliability? And David says he's not aware.
Yeah, the funny part is that there is one if the probability of disconnection is small. But in the case where you use naive Monte Carlo methods, where it's easy to check, I don't know of any deterministic method.
Okay. All right, let's stop here, and we should move on to our next talk. And thanks again, David. So you should stop sharing your screen. So the next speaker, Sagnik, should start sharing the screen. And just make sure, Sagnik, you are unmuted.
Am I?
Yeah. Okay, so our next talk is on the algorithm for the weighted min-cut problem. And Sagnik Mukhopadhyay will give the talk.
Thanks, Ajif. This is a joint work with Anupam Nanukai at Ktott Stockholm. We will start with the definition of the min-cut. This is just for completeness because Jason has already mentioned it in the previous talk. Given a graph G with n nodes or vertices and m edges with edge weights, a cut is a set of edges whose removal disconnects the graph. In the figure, the edges crossed by the blue dashed line is such a set of edges or a cut. A cut is associated with the cut value, which is the total weight of the set of the edges participating in the cut. And the minimum cut is a cut with the minimum cut value. The goal is given such a graph G, find a minimum cut of this graph. So we investigate this minimum cut problem in a number of computation models. Here is the lay of the land before our work. So in the sequential setting, the best algorithm is designed by David, which takes m log cube n time. This is a different algorithm than what is mentioned by Jason in his talk. And improvements have been made by Hensinger and others, and Ghaffari and others in very recent times, after more than 2 decades. In the cut query setting, where you're allowed to query the value of an arbitrary cut, Rubinstein and others showed an algorithm which requires near linear many queries very recently. And Asadi and Sanjeev and others observed that the cut query of Rubinstein can be adapted to the semi-streaming setting, which gives a 2-pass algorithm for the weighted for the min-cut problem. And in the distributed congest model, the best algorithm were obtained very recently by Ghaffari and others, which is sublinear time complexity. The crucial aspect of all these improvements is that all of them assume that the input graph is a simple graph, except David's algorithm, which works for weighted graph as well. So why are we not able to make progress in the weighted graph in any of these models? Is it because there is a common bottleneck that is hindering progress in all of these 3 models? So that is the question that actually motivates this paper. And before going further, a few remarks are in order. First, David's algorithm works for weighted graph, but the algorithm employs a dynamic programming paradigm and is as such hard to implement in other computation models. And the second is that all improvements that we have mentioned use techniques different from that of David. It can be argued that this is necessary. Improving or adapting Karga-style algorithm will actually yield an algorithm for weighted graph. And also assuming simple graphs makes life easier. You have a strong guarantee on the total weight of the edges of the subgraph, which you can exploit in a number of ways. So the question arises, what is so hard about David's framework? And the answer is a subroutine called the 2-respecting min-cut. The 2-respecting cut is defined with respect to a spanning tree of the graph, and a cut is 2-respecting if at most 2 edges from the spanning tree participate in the particular cut. And the goal of this subroutine is to output with respect to a given spanning tree, the minimum cut with to respect the spanning tree. It follows from David's work that if one can efficiently solve two respecting min-cut problem, then there is an efficient algorithm for solving min-cut. David showed it for the sequential setting. More or less the same theorem holds for all of the settings we have mentioned. So coming up with an efficient algorithm for the two respecting min-cut is the hard part of David's framework, or the main bottleneck. So our contribution is a new, improved, and arguably simpler schematic algorithm for the minimum two respecting cut problem, which works across all the models. And this helps us achieve one schematic algorithm for the weighted min-cut problem as well, which works across models. So this is how our result sits with respect to the previous works that I've mentioned before. We have one schematic algorithm for the weighted min-cut, and we get algorithms for all of these models with different implementation details. Two things, I should mention that the algorithm for the congest model, which is the bottom right, is not a part of this STOC paper. This is more of a recent work done by Michael Dodi, Yuval Efron, me, and Danupon, and is also available in the public domain. I have mentioned it over here because this also follows the schematic algorithm very closely. The implementation is tricky and requires many more tools. And also a similar result, that of our sequential model, is obtained independently by Garikowski and others. So I will just say a few words about the technique. As mentioned before, David's algorithm uses dynamic programming, which we try to avoid. And so we use a much simpler algorithm. And to this end, I will just put forth a puzzle to you. And this is a matrix min-entry puzzle. So the input is an n cross n matrix, M, which is with me. You don't see M, but you know the dimension n. I will also make the following promise to you that the column minimums, which are the orange boxes in the matrix, never move up as we go right. This property of the matrix is known as the monotonicity property. And the game is to find out the minimum entry of M, and the only axis that you have over M is the query axis. So how many entries do you need to find the minimum entry? And the answer is actually you need only n log n many queries by a simple divide and conquer strategy. We are left with how to connect this puzzle to the problem in hand. And the answer is tree decomposition. I will not explain more, but the details are in the longer talk and of course in the full version of the paper. And one last comment about how to play the game of the puzzle in the various computational model. So essentially it boils down to simulating the queries of the matrix in the model concerned. In the cut query model, it is trivial because the queries are actually cut queries. In the streaming model, we use the power of evaluating order n many cut values in one pass. The algorithm is parallel enough to let us do that. And finally, in the sequential model, we use the range query data structure to simulate the queries. So I will end here. Thank you.
Thanks, Agnik, for a very clear talk. We have time for questions. So there is a question from Seper. If one reduces query complexity to order n, does it improve the runtime of your algorithm? The query complexity of the matrix problem.
Sure, it does. Yeah, it does improve by a log factor. Yes, I've hidden some polylog factors in our result. It is n polylog n that you get the query complexity. If you improve the matrix min-entry problem to just linear, then it is. But this is only for the two respecting cut problem. For the min cut problem, this also goes via the cut sparsifier, and where it's not clear to me how that will improve it. So it is possible that the cut sparsifier actually dominates in this case and gives you the same kind of complexity.
Okay, so if there are no other questions at this point, we'll move on to the next talk. And then, as I mentioned earlier, we will continue the discussion after the last talk finishes. All right, so Sagnik, yeah, you can stop sharing, and Siddhant, you can start sharing your screen.
Oh, hi, can you hear me?
Yeah, we can hear you.
Cool, okay.
So just you need to share your slides. Perfect.
And yeah, I guess are my slides visible?
Yeah, so we can see your slides, and so good. So our last talk is given by Siddhant, and who is going to tell us about deterministic constructions of expander graphs.
Yeah, thank you for the introduction, Sanjeev. So this talk is going to be based on joint work with Ryan O'Donnell and Pedro Paredes, who is a grad student at CMU. So the main object to study in this talk is going to be a deregular graph G. And we're going to use the number n to denote the number of vertices in this graph. And associated with this graph G, we are going to have this adjacency matrix A. So now let's quickly talk about some properties of the adjacency matrix. It's a real symmetric matrix, so it has n real eigenvalues that we can arrange as lambda 1, lambda 2, down to lambda n in decreasing order. And since it's deregular, this adjacency matrix has a property that its top eigenvalue, lambda 1, is always equal to D. So now, let me just say a couple of things about why studying the spectrum of a graph is a good idea. And generally, it's because the eigenvalues of a graph lets us obtain a handle on certain combinatorial properties. So the simplest example of this is the largest eigenvalue being strictly greater than the second largest eigenvalue characterizes the graph being connected. And similarly, if the smallest eigenvalue is equal to negative D, this actually exactly characterizes when the graph is bipartite. So in this talk, we'll be concerned with a different property that we call expansion. And towards this end, I'm going to define the spectral expansion of a graph to be the second largest absolute eigenvalue. So one way to write this is the max of lambda 2, which is the second largest eigenvalue, or minus lambda n, which is in case the smallest eigenvalue has more magnitude. And we're going to call this quantity lambda of G, also known as spectral expansion. And one way to actually visualize this quantity is we want to come with a number lambda of G. We want to make this number as small as possible. And with the exception of the top eigenvalue D, we want all other eigenvalues to fit in this red colored interval between negative lambda of G and lambda of G. And as for why this quantity is a useful quantity to study, so first of all, it controls edge expansion, which is a certain combinatorial property of sets of vertices in the graph. And also, let's say you do a random walk in the graph. One thing you could be concerned with is how fast does this random walk converge to the uniform distribution on all the vertices, which is a quantity that we call the mixing time. And actually, the smaller the second eigenvalue, the better the mixing time, the smaller the mixing time. So in some sense, in constructing graphs, we will want this lambda of G quantity to be as small as possible. So then, so in particular, you want to construct an infinite family of graphs where the spectral expansion is as small as possible. So you could ask, how small could lambda of G be? Like, could you make it 0.99 D? Could you make it D to the 0.99? Could you make it D to the 0.6? Can you make it square root D? And okay, there's like some sort of barrier as to how small you can make this quantity. And actually, there's a particular lower bound that's proven by Alon and Bopana in 91, which says that this quantity lambda of G cannot go below a certain number 2 times square root d minus 1. So one could ask, okay, like Alon-Gopano showed this lower bound of 2 times square root d minus 1 on how small lambda g can be. But is it possible to construct graphs that actually match this lower bound? And okay, there's a long line of work that I am not getting into in the interest of time. Instead, I'm going to state, I'd say, the most related result to our paper, which is a theorem of Friedman. And this theorem says, actually, you know what, if you take a randomly regular graph, then lambda of g comes arbitrarily close to meeting this 2 square d minus 1 bound. In particular, you actually know that with high probability, lambda of g is at most 2 to d minus 1 plus a lower order term that goes to 0 as the number of vertices in the graph goes to infinity. And I think finally now I have set up the stage to talk about our result. And basically our result is, okay, so Friedman's theorem gives you a way to construct a random regular graph. But for various applications of expanders, you don't want a random graph, you want something that's explicit, something you can construct deterministically. And our result can be seen as a de-randomization of Friedman's theorem, where we give a deterministic algorithm with the following properties. It runs in polynomial n time. And if you give me an n, this algorithm can give you a graph on roughly n vertices, where the special expansion is arbitrarily close to meeting the Alon-Gopano bound. And I think with that, I shall conclude my talk. So thank you all for coming. If any questions. Sanjeev, I think you're muted.
Yeah, thanks, Siddhant. So we have time for questions. I have a quick question, which is, what's the dependence on epsilon in the runtime?
Right. So actually, the dependence on epsilon appears in like the exponent of n. So the runtime, so okay, you give me d and epsilon. The runtime is like n to the power some function f of d and epsilon. So actually, that's why you can't hope to make epsilon little o of 1 for our construction. Like it has to be a constant.
Thanks. Chandra is asking, what depends on epsilon? I'm guessing it's just the runtime, right?
Yeah. Okay, and I see 2 questions by Madhur and Salil Vatan about strong explicitness. So yeah, construction is not strongly explicit, but actually I should, let me like bring up a maybe sort of defensive point as to a construction being probabilistically strongly explicit, which is actually a notion that was coined by Bilo and Lineal. And what that means is we can sample an order log n length seed. And from the seed, like once we have the seed in hand, we have a strongly explicit construction. So it's strongly explicit, but randomized.
Okay, so there is also a question on any ideas on getting Ramanujan instead of almost Ramanujan graph.
Right. So these techniques, at least the techniques we used, would run into a barrier since they try to de-randomize Friedman's theorem. And I guess Friedman's theorem does have like an almost Ramanujanness to it. So yeah, that's certainly a question that needs new ideas.
So there is another question. Is there any hope of having space-efficient constructions for these graphs?
Right. So I'm assuming space-efficient here means like strongly explicit, where you're able to navigate this n-size graph in polylog n space. So I'd say the same thing as what I said in response to Madhur and Salil's questions.
Okay, all right. So I think we can maybe, so let's thank all the speakers. And so we can stop recording the session at this point, but we can continue with the discussions for another 15 minutes or so, which will be just an informal discussion where people can ask questions on any of the 4 talks to the speakers. I think we have all the speakers here still. So Zihan, you can stop live streaming now. And so the formal